Hello, Jeff Disher here again. Today I'm going to take a break from some of the open autonomy demos I've been doing to get back to some of these little talks I've been doing. So today I'm going to talk through software execution models. Now, what I mean by that is, in case you've ever heard a software developer or even some just like online news site or something talk about the differences between asynchronous, synchronous, and multi-threaded execution, that's what I'm going to be talking about today. That's what I mean by execution models. So first of all, synchronous execution. Now this is the simplest case. It's just that you do one thing at a time. So you finish task A before you start task B. See this everywhere. It's a very easy one to understand. There's also asynchronous, which is you're allowed to do multiple things at once as long as they don't require your direct interaction. Sort of like anything that takes a long time of you waiting around, like waiting for the network or something like that. So what it means is you'll start A and B, and then you can wait for them to finish later. But they can both run at the same time because they don't require your direct interaction. Multi-threaded is like asynchronous, except that it's based on the assumption that you can't just wait for those things to finish. They're not long-running tasks like a network operation or something like that. There's something like, okay, draw this picture, something that actually requires the CPU to be directly working on something. So multi-threaded tasks actually can use multiple CPUs or multiple cores in your computer to actually get through tasks faster. So that means you could be start and finish A, and simultaneously start and finish B. And these would actually run on different cores. So I'm going to use what I call the breakfast analogy to explain what these things mean. It's just going to be a simple real-world example of how a bunch of asynchronous and synchronous tasks can be how you can schedule them differently and perform them differently in order to get through them to get through them faster by using some of these different ideas. This comes down to a basic kind of morning routine. You wake up, you have a shower, make yourself coffee, make yourself some toast, and then you sit down to eat breakfast. So this kind of very simple example, but it's got there's enough little pieces of this that show how you can actually benefit by thinking about this in different ways. So of course the synchronous example is the simplest one. You just do one thing after another. You wake up, have your shower, then you start the coffee maker, you wait for the coffee maker to finish, for it to brew the coffee, then you start the toaster, then you wait for the toast to pop up, and then you can sit down and eat breakfast. So this is fine, it works, it's obvious how it works, just one thing after another. And it doesn't really matter what order you do these things in, they kind of all end up being finished at some point. There's no real having to think about how do I coordinate this. It's very, very simple. The problem is, though, there's a lot of time that you spend just kind of waiting around doing nothing. Like the time between starting the coffee maker and finishing the brew cycle, that's going to take a while, and you're not doing anything in the meantime. You're just standing there. So this is wasting a lot of time that you could be spending doing some sort of active task of some sort. This is similar to what you'd see in like a C program. And of course, C programs can also do asynchronous and multi-threaded operations as well. But it's a good example of sort of one of those programming languages that's the do one thing, then do another, then do another kind of model is the one that it lends itself most easily. So asynchronous is when you try and solve this problem of having all this weird dead time, where you're just standing around waiting for things to happen and not actually being directly involved. So, for example, you might immediately after waking up start the coffee maker and start the toaster. Then you get into the shower, because realistically, you're just waiting for these things to work anyway. You may as well be doing something that would take all your attention, like having a shower, instead of just standing around waiting for them, seeing as you have to do that anyway. And then once you get out of the shower, you can finish waiting for the coffee to brew and finish waiting for the toast to pop, assuming they haven't finished already, because they might have done that entirely while you're in the shower. In fact, they probably would. Then you can sit down and eat breakfast. And you can see this example is better because we're not actually spending as much time waiting for things to happen while there's something else we could be doing. So it works fairly well. Now the problem, of course, is some of these things still do take some time. Starting the coffee maker takes some time. You have to put everything together, get filters out, things like that. So there's still some things that we are having to do which seem like, wouldn't it be better if we could somehow not have to do that work? And we could only worry about the shower, because that's probably the task here that takes the longest. So this is what you'd see in, for example, JavaScript. Because JavaScript is written to be running inside a web browser and trying to do things like network operations, which take a long time but don't require any CPU power, they just kind of wait for things to happen. It's based entirely around this idea of you're going to be doing a lot of asynchronous operations. fact, if you ever hear anyone talk about AJAX, the asynchronous JavaScript and XML, that's what it means. They're actually doing a network request asking for some kind of XML info or something, actually that's often not XML these days, but something that's coming across the network slowly. So it happens asynchronously. So the multi-threaded example is, okay, how do we better split these things out? Is there any way we can actually do some of the active tasks at the same time? And the answer is yes. In this simple example, we're going to assume that you have, say, a servant that's actually going to help you do these things. This is actually a fairly common model that you'd see in certain kinds of software development, where you often have what's called a master thread and then potentially many slave threads, which all kind of get their instructions or their marching orders, so to speak, from the master. So first of all, in this case, you'll have the master person, which is you. You wake up and immediately you get in the shower. Once you get out, you sit down and wait to be served by the servant. And then you can eat breakfast. Meanwhile, the servant, while you get up and have a shower, they get up and start doing the work, the other work. They make the coffee, they make the toast. Whether they do these things one at a time or asynchronously, or whether you have multiple servants doing them, it doesn't really matter. The idea is that these operations have been taken out of your critical path, as it's called. You're no longer having to specifically do these things, you just wait for them to happen. And this is similar to what you'd see in, say, a Java program. While it's possible to do multi-threaded programming in a lot of languages, like C, for example, you can't do it in JavaScript, but in C and Java, Java is a very good example of an environment that's got a lot of support for being able to do this, so it makes writing multi-threaded programs easier, because there's lots of reasons why this is difficult. But as you can see, in this case, we've managed to remove that extra cost of the starting to make the coffee, putting together the filters and everything, from what you have to do. So now if having the shower is the thing that takes the longest in your morning, well, the entire cost of all this creating the breakfast has now been removed from the amount of time you have to spend getting ready in the morning. So by adding this extra servant, or in the direct CPU analogy, adding a task that can run on another core, we've actually made things measurably faster, because it's going to take you much less time to get through all of this now, because you're not doing as much of it. But there's a bunch of concerns that come along with these things. For example, synchronous, it's the easiest case. It's just do one thing, then another. You don't require any planning or coordination. In fact, in this example, it doesn't even matter which order you do things in. Everything just kind of will take a certain amount of time, and that's just the reality of it, and that's fine. Just get it done. The problem is, of course, it wastes a lot of time, because there's some of these operations that don't require your direct attention. So doing them one at a time could be a problem. Asynchronous is a bit harder. Now, the reason is you actually have to plan what you're doing. For example, in that other case, we had to figure out, okay, well, we need to now decide to start things before we start other things, so that we can actually hide the costs of some of the operations inside the time we're already spending doing others. And it's got a limitation as well, in that you can still only be doing one direct activity at a time. Like while you're in the shower, you can't also be getting the coffee maker going. But if you got the coffee maker going before you got in the shower, then it can be doing its background operation while you're there. So multi-threading is the hardest, and there's lots of reasons for this, but that's hours of lectures on their own, and they're quite technical. So the details that you just need to understand from it are, you require a lot of planning and coordination. Yes, I have to know the order to do things in, but I also now need to know who's going to do them and how they're going to notify me that they're finished doing them. So this kind of coordination adds extra complexity, and in actual software it adds a lot of complexity, more than you'd think. So the benefit, of course, of this is you can do now multiple activities at once. Now you can have all those extra cores in your CPU actually doing other things. So this is taking it to sort of that next level. So anyway, I hope this explained what some of these terms mean when people are talking about these things, or whenever you see them in articles online or weblog posts or anything like that. As before, send me an email at jamdisher@gmail.com if you have any questions or concerns or comments, or just post them here to this video, and I'll get back to you. Thanks.